So we are gonna go ahead with these. I think yeah. So yesterday, what I did was I managed to fix the stuff uh, with the shapes, and I think now I understand that better. Makes sense that you kind of have to maybe initialize things like that, so it's understandable that it's one row and certain amount of columns, so you can address them like that. That's the difference. It's just basically the way you address them. Cool. But what it is that we're trying to do anyway, right? So we have, uh, yeah, we're trying to print stuff. These are W. So Python test. Python test.py. So we have X. X being sort of like, yeah, something that's like 10 dimension 10. Then we have W. Then we have B1. This thing's been initialized. Okay, yeah, so this has been initialized with zeros. Should be not initialized like random, but anyway, I think W2. So these are essentially like W1 and W2 are essentially the two core matrices, right? Two core tensors, and then what the forward pass does is calculate some Z1 like Z1 as the dot product plus B1. That is just saying that is just some sort of like a kind of like a projection finding the two. Then okay, we understand there's some sort of like activation thing. So just because tangent tan h is basically non-linear, so we're applying these operations. Okay, but we're missing something here, aren't we? Z2. I haven't done Z2. So if, no, but if you don't do Z2, no, we have to do Z2. Use A1, W2, B2. So okay, so actually that's this A1, and then I guess it suggests a softmax probabilities. Softmax probabilities. Yes. So x1 times w1 2b2 z1, and then we should print z2. Two. Z2 is 3 dimensions. It's only 1, 3, shape 1, 3. Actually, pretty print Y as well. Okay. So A1. A1. So we have what the forward pass is doing is the whole operation. So forward pass is doing Z1 and A1 calculation. X. So X is like it's the size 10. It's it's 110. And this is basically 10.5, right? So the result, that's why and that's why this can then be broadcasted. So and the result is basically 5 dimensions because it's 10 tens. It's like boom, pam, boom, 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 boom. So that's how the dot product is working. Which is fine because that's what we want. So we're kind of going from 10 dimensions into 5 dimensions, and then the output size is 3 dimensions. Right? Let's say that we have like a 3. Yeah, that's our choice, right? So Z2 is basically, and I guess essentially these is irrelevant. As in, like, this is just what you're. So this is just the topology of the network, right? So this is just how you. This is just how you can change that, and that's gonna probably change how easy the network to train is, right? This has no. This is just kind of laying out a basic mathematical foundation. Yeah. And then for the diff, so this is kind of really what matters, right? So we have these. I don't know. I think the biases shouldn't be initialized to 0. I think we should also just initialize them to like random. I think it makes more sense. So what is better? So no, they are not zeros anymore. Okay. So this is kind of fun in a way, right? So then this is what we're kind of doing. Okay, so the diff, right? So here we're simulating. What I want to do is, okay, so here what we're doing is we're simulating a, first of all, so we're simulating a specific run and a specific. So where one element of the diff is going to be 1, because essentially the diff is what's saying is basically the probabilities minus the truth, right? Saying is the probabilities minus the truth, the predictor minus the truth, we're gonna have a 1 somewhere where we predicted something, but it was not a prediction, and a -1 where we didn't predict something, where we predicted 0 probability and it actually had 1 probability. And of the where one element of the result 1 because we wrongly predicted it as output, and another is -1 because we did not predict it well. I think that's kind of how we can simulate that, right? So here these at 1, okay, so these, yeah, but that's kind of, here's a problem, right? Because what we can do is like, okay, so right, so it must be different. So two different generate two different random indices for the I thought you could just do this in line here, but we can try here. So I guess this obviously can overlap itself, right? So that is the right. Now let's run it again. Yeah. Let's run it again. Okay, cool. So then we start with the backward pass. Okay, that's where it kind of probably gets tricky. But I think it's good so far. I think we have a good simulation of the forward pass. It's basically a combination of like a dot matrix plus a bias and then something that's not linear, and then another layer of dot matrix plus this stuff. This also just basically converting it into the probabilities. Now the backward pass is basically saying, I guess this is where we don't really know whether we're doing this correctly or not, right? So first of all, we're saying we have these at 2, so we have these. This is kind of the difference, okay? So I think we argued in the past videos already that okay, that is an okay thing to do. I mean, as in like just because our optimization function is a logarithm, then the subtraction makes sense in this case. Now it's been a while, so I'm doubting this again myself, but let's see if that leads to an explanation of this as well. But even if I didn't know what I'm doing, like I would actually go off from the assumption that, well, it kind of looks okay, right? I mean, you're looking at how far off you are, and then you're trying to kind of compute something that helps you modify a function, that helps you modify the matrix so that you kind of get there, right? Because essentially, this is telling you that you shouldn't touch these elements, and this is telling you that these elements should be slightly adapted, right? But now, I guess what my problem here is that there's some sort of metric or tensor magic that I'm not understanding well in terms of how to translate this, right? Because if I have these at 2, okay, let's take a look at DW2. So what do we use DW2 for? DW2 is something that we're going to use then directly to adapt W2, right? Because that's what we ultimately want to do. We want to adapt W2, W1, B1. Okay, exactly. Why are we even using A1? That just makes no sense because A1 is used to calculate A1. A1 is used. A1 is used to calculate W2. Okay, I understand that. But I shouldn't really care. Should I? This is kind of the question here, right? So why can't I modify W2 directly? That would be my intuition. My intuition would just be to say to apply this directly in a way. Because yeah, why involving A1 at all? I understand the idea of doing something like that. I understand you want later on the change to be like from a learning rate perspective, you know, reduced so you don't make too big changes. But essentially, if what we have is these, right? We have these as a x times W1, and then the result, you can think of these just like ignore that there is the fact that there's an A1 in between. It's just the result of this operation 1. So we have an operation 1, and then the result of this operation 1 is used to the to operation 2. Is used to the second matrix for to then calculate Z2. So why it just makes absolute no sense. What I want to do is I want to just modify W2 directly. I don't want to like why. So now I have two options, right? So either I just go with so we have two options. So either we go with my intuition or we try to dig into like why would Ghostwriter suggest that in the first place, right? Because my suggestion here would be then my suggestion would then be here, and then I wanna of course test these changes by probably running again, sort of simulating another forward pass, right? So that's probably what we want to do. So I want to do here then a simulating sim to do sim another forward pass with the corrected matrices. Okay. See if that has anything. But that's just like so okay, so we maybe let's I think I know what is happening. So let's kind of go from the fact that what we need to do is we need something that transforms DW2 so that we're getting closer to like to 000, right? Here. We need something that transforms DW2. So if it has to transform DW2, it has to multiply the sorry, the transform W2. So if it transforms W2, it has to basically be of shape A, right? That's it. Because we wanna. It doesn't matter. I mean, actually, what we want to do. No, yes and no. Probably yes, because this is another thing that I was not like. This also makes kind of no sense in a way, right? Here we're just saying is like, oh yeah, no, okay, you have a matrix. So either you have a DW2 size thing that then you're kind of like minusing it, right? Because it has the same shape, and so you can exactly do a subtraction. That would be my my intuition would just be DW2 needs to have the same um, the same dimensions or the same shape like W2, right? Which I don't think here it does. I think here, because you're doing an A1 multiplication, you basically have something that then you broadcast, which just absolutely makes no sense. Like you have something that is just like five dimensions in our example, small example, and then you kind of broadcast on all the other rows. That is kind of limited. It feels limiting, right? So to me, I think this should kind of have exactly the same size. So what we should do rather is, but how would you do that? So how would you do that at all? How would you do that at all? How would you do that at all? Because W2 then leads to W2 is hidden size, output size, W2. And when you multiply it by A1 is what turns it into Z2, that it's kind of what has the shape. It's what kind of has this shape. So maybe that is why we're involving A1. Because we want to affect, but we want to affect our multiplication, right? So we can either base it off A1 or W2. Why? I don't see why I wouldn't. And A1 is just something that you're calculating, so you shouldn't be basing it at least off of anything. You're just trying to train W2 and B2. But how would you do that? So, and all I have is just these, right? So we have one thing, we have one tensor that we're multiplying with another tensor. I'm just going to use this notation, right? And we're getting a result that we want to correct. We're getting a result that we want to correct, right? If we want to, I think thinking if we just want to this result to be like minus some kind of delta, right? We want to apply a minus delta to this result, and then you kind of have to apply this minus delta here as well, in a way, right? Making sense? Am I making sense? Yeah, but what? Like, but okay, so we know D, right? We kind of know D. Now, how can we blend? The thing is, how can we blend this minus delta in here, right? Because that is essentially the shape. Oh, this is hard. This is hard. This is hard. This is hard. This is very hard, actually. This is very hard. Let's see if Ghostwriter can give us some guidance here. So do you have an idea? So do you have an idea on how can I modify, how can I calculate the change in W2 that I have to make in order to influence the result using the basically the difference, the dW2 probably makes no sense for Ghostwriter at all. Take a layer, like a gradient. Change in weight is calculated by multiplying dW2 by the learning rate. Yeah, but you can't do that because you can't do that because you can't do that directly because you can't do that directly, right? Each element of this matrix is the weight of a connection between two neurons, one from the first layer and second layer. The rate of change of the network's loss function with respect to the weights in W2. The purpose. That's the problem. That's not like DW2, right? DW2 is sort of the rate of change with respect to just the outputs. There's nothing to do with W2 here. Like that whole thing assumes what I just said. Assumes that DW2 has the same shape as W2. That is the main issue here. Is that these, right? It's DZ2, of course. It's not DW2. It's DZ2. So we need to actually compute DW2, right? What I have is DZ2. Like DZ2 is just basically saying that is the difference between yeah, Z2. So that is the difference, and it's really actually dy, right? That is just the difference between. It's just the difference between the outputs. Is the difference between the outputs, but how do you get? Okay, so maybe the better question is if I am starting by calculating the gradient of the upper layer. I go from that gradient to the gradient of the hidden layer weights. That is the thing, right? That is what's happening here. So what I have here is DZ2 is the gradient of the output layer. So the hidden layer weights, you have to apply the chain rule to propagate gradients. Okay. Chain rule. So we're getting the chain rule. And I guess this applies because of how the forward pass is built, right? Because this is like these times, like you have like a multiplication of functions, and so the derivative of some of the elements, I have to recap what the chain rule really is telling me. Start by calculating the gradient of loss with respect to each output. In your case, since you're dealing with the softmax output, assume a specific type of error, you're subtracting the one hot cone. Then you compute the gradient of the loss with respect to the weights. It's calculated by taking the dot product between the transposed activation values. It does include A1 here. It's because of the chain rule. Okay, so we really need to get into the chain rule. That's the next thing, right? So let's do that. To do rule back propagation. That's gonna be the next one. Chain rule back propagation. Yep. See you in the next one.